fit that to your CFT shirt.
Okay, thank you.
Does CFT stand for something else in this context?
It does. It stands for California Federation of Teachers.
Okay.
But I just had to get the shirt.
Nice. I also am in a C state, so I wonder if I can.
Yeah, you should look for it.
Use that.
I mean, I hope they have just as appropriate looking a logo.
It's a nice little logo.
Yeah. Yep.
Now we need like the Alabama Department of Science to like also have a shirt that can just someone else.
That's right. Yeah, it's a good idea.
Okay, I think I'm gonna call.
Okay.
What do you think? It's too busy, or yeah. Well, I mean, he has 3 kids, and he has a lot to take care of. Okay, I'll talk to you one later. Ready to be introduced? All right, well, for the last lecture of the day, this is our first lecture, the last beginning of a lecture series. So we're very pleased to have back David Simmons-Duffin from Caltech, who's going to be talking to us about CFT and observables on a null plane. David.
Okay, thanks a lot. It's great to be back here, but seeing a lot of new faces. In these lectures, we're going to talk about an interesting class of operators that are expected to make sense in a general QFT. But for simplicity, I'll mostly be talking about conformal field theory. And these are called various things in various contexts. Sometimes they're called light ray operators. When the light ray operator lies along future null infinity, these have the role of detectors in collider experiments. So I like to draw a kind of pseudo Penrose diagram for Minkowski space where I don't mod out by the sphere. Okay, so the idea of this diagram is that the interior is Minkowski space. This is future infinity, sometimes called I plus. This is past infinity, I minus. This is spatial infinity, sometimes called I0. And then you have future null infinity. And I don't know how to draw the funny symbol people use for this, so I'm probably going to get it wrong. Scry plus and scry minus is past null infinity. And the idea is that in this diagram, it makes clear that there's a sort of rotational direction. When you have radiation coming from the interior of Minkowski space, it can escape in different directions. And the possible directions that it can escape are parameterized by a celestial sphere. And if we're in a d-dimensional theory, the celestial sphere is in SD minus 2. So the radiation can escape in different directions on the celestial sphere. And a light ray operator becomes a detector if it lies along future null infinity. So if we have a light ray operator lying along a null ray along future null infinity, then it's a detector. So and actually, we'll find out in these in this course that light ray operator might be a little bit of a misnomer. It might be better to call them light cone or light sheet or null plane operators. And that's because they will be labeled by a light ray, but it will turn out that there isn't an invariant way to really localize them on that light ray. And in general, we have to consider the entire light sheet that they're on. Okay? So that's the reason for the words null plane in the title of the lectures. And this is something that we'll explore in this course. So these light ray operators are not very well understood in general. So in this course, I'm going to focus mostly on some concrete examples. We're going to be looking mostly at the Wilson-Fisher theory, which is maybe the simplest perturbative conformal field theory. And we'll construct light ray operators explicitly in that theory and try to explore them a little bit. And the idea is that this is a precursor to understanding how light ray operators should behave in a general CFT. But that story is not yet written. There'll be lots of open questions, and I hope to tell you a little bit about some of them. Okay? All right. And by the way, I absolutely invite questions all the time during the lectures. Please stop me anytime you like. I love taking questions in the middle of the lectures. So are there any questions? Yes?
How did you get the 8th paper?
First, you go to archive/local time. You sync up your clock. And then you get ready to submit. And you wait there in front of your computer, and it helps to practice clicking. Anyway. All right. Right. Thank you for pointing that out. So a lot of the material is based on this paper and references therein. So what I'm going to be doing is trying to walk through basically the introductory sections of this paper and fill in the material that you need to understand them. Okay? All right. So let's get started. So we're going to start by looking at an even simpler theory, the free boson, and defining our first set of light ray operators in that theory. And by the way, I should say that in a conformal field theory, there's nothing special about future null infinity. It can be mapped by a conformal transformation to any other null plane. So in a conformal field theory, there isn't really a distinction between a detector, which is an operator living on future null infinity, and a general light ray operator, which is an operator that lives on a general light sheet. Okay? So that's mostly the context that I'll be thinking about. But it is very convenient to work in the so-called detector frame, where you put your light ray operator along future null infinity. So that's what we're going to be doing for a lot of these lectures. Okay, so let's start by talking about detectors in the free boson theory, free scalar. So the most important detector in this theory, and probably any theory, is the so-called energy flux operator, which I'll write as E2, and it depends on a direction n, which is a point on the celestial sphere. And in words, what it does is measure the flux of energy propagating out in that direction. So one way to construct it in the free theory is as follows. So we can start by writing the field as a sum of creation and annihilation operators. So it's going to be an integral over momenta. And this integral is going to include all momenta in the future null cone, inside the interior of the future null cone. So this notation here, actually maybe it shouldn't have P0. So this notation here, P greater than 0, means that P is in the interior of the future null cone. Sorry, not interior of the future null cone. I do want this. I'm going to have a delta function putting it on the null cone. Okay, and then we have creation and annihilation operators. And I'm using here a relativistic normalization for the creation and annihilation operators, where the A's and A daggers transform in a simple way under Lorentz transformations. So if you have a Lorentz transformation, then the momentum inside the creation operator or annihilation operator just transforms linearly. Okay, and this is a little bit different from the normalization often used in QFT textbooks, but it would be much better for our purposes. And just for completeness, we can write the commutation relation in this normalization. It looks like this. 2p0, there's some 2 pi's that I'm not going to bother writing, but that you can find them in the notes, which I will post online. Okay. All right. Good. So the idea of the energy flux operator is we can start with an expression for the Hamiltonian, and then we break the Hamiltonian into different pieces corresponding to different angles on the celestial sphere. So the Hamiltonian in this normalization is an integral over spatial momenta of just a dagger times a. And here, when I write a as a function of spatial momenta, I mean evaluating at the null momentum p corresponding to that spatial momentum. So a of p vector is a of the 4 vector absolute value of p, comma p. Okay, hopefully that notation isn't too confusing. And you might be wondering, wait a minute, what happened to, isn't this supposed to be energy? Aren't we supposed to have a factor of energy in here? Well, that's related to the fact that we're using a different normalization where the energy appears in the commutation relation of the a's. So you can check, you should check for yourself that this actually does have units of energy, okay? And is the correct expression for the Hamiltonian in this normalization. So to get the energy flux, we just split this into different contributions corresponding to different angles. So we want something that integrates to the Hamiltonian when we integrate over the celestial sphere. That should be h. And, but furthermore, this should only depend on creation and annihilation operators associated with momenta in the n direction. Okay? So the solution is that this energy flux operator is an integral over energies with a particular weight like that. Okay, and in words, what this operator does is it counts particles propagating out to future null infinity and weights them by their energies. And the fact that this is a factor of e to the d minus 2 as opposed to just e has to do with the mass dimension of the creation and annihilation operators as we've defined them. Okay, but when you see this expression, you should think counts particles weighted by energy. Yeah. Yeah, so there's a 2 subscript, and I'll explain that in just a minute. Good. Okay, so this is one very explicit definition of the energy flux operator in the free theory. We can give a different definition in terms of an integral of the stress tensor. So the idea is that the energy flux operator is a limit, a large radius limit of an integral of the stress tensor, where we take the stress tensor with particular components. So it's an integral over time from 0 to infinity, ni t0i of t comma r n. So what's happening here is r to the d minus 2 times ni t0i is the angle element in the n direction times the current for energy, right? The current for energy is T0 mu. And so we're contracting the mu index with with n sub I. So we're measuring the flux of energy in the n sub I direction. And then we integrate over time in order to collect all the radiation that arrives at future null infinity. And then finally take a limit as r goes to infinity. So in terms of this Penrose diagram, what's happening is that we're starting with the stress tensor at some radius, and we're integrating over time. So we end up with some kind of integral of the stress tensor, which ends up at future infinity, like that. And then, as we take r larger and larger, we're moving the detector farther and farther away from the origin. And on the Penrose diagram, we get something that looks like this. And then finally, in the limit that r goes to infinity, we end up with some kind of integral of the stress tensor along future null infinity. So you can check, and it's an interesting exercise to do, that if you write out the explicit definition of the stress tensor in the free theory, and you plug in this expression in terms of creation and annihilation operators, then the limit of this integral actually does reproduce that. Okay? Yes?
I mean, I know why the units of energy are T minus 2, but aren't we like penalizing the ground states of the Hamiltonian more than we need to?
Well, so the question is, are we penalizing the ground states of the Hamiltonian more than we need to? What we're doing here is we're trying to define an energy flux operator, and the ground states just don't have, the ground state doesn't have any energy flux. So it makes sense that this operator penalizes the ground states. You might be interested in other operators that measure more interesting properties of low energy states, and then those would be weighted by energy differently. Other questions? Yeah?
What is the goal in studying these operators?
Good. Okay. So maybe the question was, what is the goal? So this is a model of a calorimeter. And when you have a collider is in part built by a bunch of calorimeters. So this is what a calorimeter looks like as a quantum operator. And by constructing operators like this, you can ask questions like, what will a collider measure? What does a collider experiment look like in quantum field theory? I want to hold off on fully answering your question until just a little bit later. Okay, but that's a great question. Like, what is the point of these particular operators? And so hold on to that question and remind me about it in a little bit. Other questions? Okay. Good. So this is an example of something that you might try to measure in a collider experiment. But there's more that you might try to measure. And so what other kinds of detectors can we write down? What other kinds of operators associated with future null infinity can we write down? So one simple thing that you might try to do is, instead of measuring the flux of energy, you could measure the flux of a power of energy. So we could define something that I'll call E sub j, which counts particles propagating out in the n direction, but weighted now by a non-trivial power of their energy. And I'm going to write the non-trivial power as j plus d minus 4 a dagger times a. Okay, so if E sub 2 weighted particles by energy, E, then this is weighting particles by e to the j minus 1, right? Because that's the difference between this power here and the one in our expression. Sorry, did I mess up the powers? I did. This should be a 3. Probably. No, it's j is 2. Oh yeah, sorry, I didn't mess up the powers. Okay, good. Okay, good. So the powers are correct. When j is 2, this is equal to that. When j is 2, that's weighting particles by E by energy E. So this is weighting particles by e to the j minus 1. So I said it correctly the first time. Okay, so in words, it counts particles weighted by energy to the j minus 1. Okay. So why am I using this funny labeling in terms of j? Another definition of this operator is as an integral analogous to this one of a different local operator along future null infinity, which is a spin j current. Maybe I'll use O 0, 0, 0 I of t Rn, where this operator O mu1 through mu j is a spin j operator built from phi and its derivatives. So it roughly has the form phi and then a bunch of derivatives, j derivatives phi. And if we're in the context of conformal field theory, we need to take some linear combinations of derivatives in order to get a primary operator. And that won't really be important for us at the moment. What you should do is just think of this O as being a 2 phi operator with j derivatives. Okay? So this is the reason for this funny labeling here. Here, j corresponds to the spin of the operator that's being integrated along future null infinity. Okay? So E sub 2 is the integral of this spin 2 operator. Okay, questions?
J has to be bigger or equal to 2.
That's right. So in the free boson theory, these operators exist for even j. Actually, it also exists for j equals 0. So we could consider all of these cases.
Sir,
Yeah.
in what sense is that operator integrated along the null rate infinity?
Good. So far, I just drew a picture. So this is a picture of what these integrals look like on the Penrose diagram. And you can see that even though it's a time integral, when you push it out to large radius, it's really running along future null infinity. And we'll be much more precise about this in a little bit, okay? But for now, you can understand that at the level of pictures.
Because the arguments of the stress tensor is not null, right?
That's right. That's right. But future null infinity is a null plane. And you'll see why in a little bit. Yeah. Good. So if you take j to be odd, then you can't find a primary with j odd in the free boson theory. Wait, am I saying that correctly? Yeah, that's right. So for example, phi d phi is just the derivative of phi squared.
Right, but so that's something wrong with the lower formula. What about the middle formula?
Oh, this formula. Yes, that's right. So that's going to be an important point. That's the point I'm going to make next. So this formula makes sense for even integer j. But this formula makes sense not just for odd j, but actually for any complex j. And this is going to be a key observation for us. Energy is positive. So this operator actually makes sense for any j, because we can take a complex power of a positive number, and it's unambiguous what it means. So what we have here is an interesting situation. We have a family of operators in the free theory labeled by complex j. When j becomes an even integer, these are integrals of local operators. When j is not an even integer, they're not. They're something else. So it's a family of operators that interpolates between local operators in some sense. It doesn't literally interpolate between local operators, it interpolates between integrals of local operators like this. And this is our first example of something called a Regge trajectory. So it's a family of operators with a complex parameter J that interpolates between, and I'll write null integrals, null integrated local operators. And I didn't really explain why this is a null integrated local operator except at the level of pictures here. So that was your question from earlier. And we will explain that in a little bit, OK? But for now, I'll just write out what it actually is. So this is interesting. We found this interesting class of operators in the free theory. These operators together are sort of maybe a better model of what a collider does in the free theory, because you can detect particles and you can just measure their energy. In particular, you can take weighted sums of their energies with any powers that you like, because you literally know the energies of the particles. So together, these families of operators are sort of a better picture of what a collider can do in a free theory. OK, yes? The question is there a sense in which the epsilon j's are independent or dependent on each other? That's a good question. So in this case, they're related by analytic continuation in this parameter j. And that's the best I can say at this point. Other questions? Yeah.
If you think of a real world collider, it won't be situated at, say, infinity. So do you need some nice follow-up condition for T0 for it to be physically sensible, related to
Good. So I was going to talk about that a little later, but maybe I'll zoom forward a little bit. So the question is, in a physical collider, the collider is not actually located at infinity. The right way to think about this, I think, is in the sense of an operator product expansion. So in an operator product expansion for local operators, you have some local operators at different places. And you can write them as a sum over operators that transform in a simple way under symmetries. So for example, operators at the origin transform in a simple way under dilatations. So you can do an expansion where you replace a bunch of operators in different places with a sum over operators at the origin. Similarly, we should do an expansion where you start with a physical collider, which doesn't live at infinity, and you expand it around operators that transform more simply under symmetries, which are operators that do live at infinity. Okay? And I'll write that down in a little more detail in a second. Okay? All right, so we have a Reggie trajectory, but you might think, wait a minute, but maybe this is just something special about the free theory. What happens when we turn on interactions? Like, can we find these kinds of things in an interaction theory? For concreteness, let's turn on a phi-4 interaction. As a reminder, the beta function in d dimensions is minus epsilon lambda plus this famous 3 lambda squared over 4 pi squared plus higher order in lambda. So we're going to turn on interactions and ask whether we can still make sense of these things. So, OK. So first of all, when we turn on interactions, the energy flux operator is still fine. It has a definition in terms of an integral of the stress tensor. And this definition, of course, continues to make sense in any QFT. So we don't have to worry about that. But we should worry about this middle definition here, where I say that J can be complex. Does that definition make sense in an interacting theory? Well, physically, the answer is no. And it's due to a physical effect called splitting, soft and collinear splitting. When a particle propagates out towards null infinity, interactions can cause it to split into other particles. And in fact, in a conformal field theory, this will happen an infinite number of times before it reaches null infinity, because there's a dilatation symmetry. So it will split and then split and then split and then split and then split. In this splitting process, energy is conserved. So under splitting, okay, can draw a little cartoon. We have a particle, it splits into particles, and then that splits into more particles, and so on, as it propagates out towards future null infinity. So in splitting, energy is conserved. E is E1 plus E2. And this is important for the energy flux operator to still make sense. So the energy flux operator doesn't care how many particles it's measuring. It just cares about weighting them by their energy. And that doesn't depend on how many times the particles have split. So it actually still, it's OK. However, powers of energy are not conserved. So if we raise e to the j minus 1 for some general complex j, this is not in general equal to the sum of e to the j minus 1 for the two constituent particles. So what this means is that this EJ operator, as we defined it, is not IR/collinear safe. Okay, this is terminology that you might hear in the context of collider physics a lot. You have to make sure that the things you're measuring are IR safe. Okay, and what that means in practice is that they make sense even in the context of this splitting process. So for example, in a CFT, if you tried to actually measure this E sub j for general complex j, you would get, if you just used that naive definition, if j is bigger than 2, you would get 0. Because you'd start with some energy, it'd split into lots and lots of little pieces of energy, and then you raise that to a power bigger than 1, and so you just get a sum of a bunch of very tiny things. And if j is less than 2, you get infinity. Okay, there was a question.
So if beta is non-zero, then how you can't talk about a CFT, right?
Good, good. So a lot of the things that I'll talk about are cleanest in the context of a CFT. So good. So I should have said that. So we're going to, a lot of the time, focus on the Wilson-Fisher fixed point, which is where we go to a 0 of the beta function. So that looks like this plus higher order in epsilon. And most of the statements I make are conceptually cleanest in that context, although not all of them will depend on a CFT. But thank you for pointing that out. So this is the Wilson-Fisher fixed point. OK, so this naive definition of E sub j doesn't make sense in an interacting theory because of this phenomenon of splitting. So OK, so how should we make sense of these things? And to think about that, I think it's useful to revisit the case of local operators. And we're going to try to draw an analogy. So in a CFT, we have a nice non-perturbative definition of a local operator. So the idea is to use radial quantization and the state operator correspondence. So what that means is that the space of local operators is equivalent to the Hilbert space of the theory on SD minus 1. Now, one nice thing about this definition is that it's completely intrinsic to the CFT. It doesn't make any reference to any microscopic degrees of freedom that the CFT might emerge from. Another thing about this definition is it makes clear that the local operators are theory dependent. Right? The space of local operators and their quantum numbers depends on the theory. You can't decide beforehand what the quantum numbers of your measurements are going to be. You have to find out what they should be. Okay? So in words, the local operators are the things you can measure at a point. And the things you can measure at a point are determined by the theory. Okay? You don't get to pick them beforehand. You ask the theory what they are. So now let's think about this in the context of a path integral construction of a CFT. So we have some path integral, let's say with some Lagrangian and fields and everything. So we might try to write down, so we might try to measure Baire operators, which are products of fundamental fields. So for example, the operator phi squared. So if you try to do this, you quickly find that the Baire operators are not the good operators. The correlators of Baire operators are divergent. They're UV divergent. And you need to take careful linear combinations of Baire operators to access the actual local operators of the CFT. Okay? So the Baire operators are not good operators. The good operators depend on the theory. We need to do a calculation to figure out what they are in terms of Baire operators. Another way to say it is that in trying to measure Baire operators and trying to compute their correlators, you're trying to measure the wrong thing. Okay? And you need to figure out what the right thing is. So for concreteness, let's look at exactly how this works in the case of phi squared. Okay, so let's look at an example. Phi squared in the Wilson-Fisher theory. So we can look at a correlator of phi squared, this Baire operator. So for example, we can look at the correlator phi squared with a 3-point function of phi squared and phi and phi. And this, of course, maybe even better would be a 2-point function of phi squared, but this is going to be ever so slightly simpler for our purposes. So we're going to do the 3-point function. So as a reminder, the Feynman propagator in position space in d dimensions looks like this. So there's some gamma functions and some factors of pi, and then x to the d minus 2. This is just the Fourier transform of the familiar formula 1 over p squared plus I epsilon. And we're going to work in the MS bar renormalization scheme. So in MS bar, and we're also going to work in Euclidean signature for now, for this calculation, although we're going to do a lot of stuff in Lorentzian signature later. So in Euclidean signature, a vertex gets a factor of minus lambda mu tilde to the epsilon, where mu tilde is this funny renormalization combination of the renormalization scale mu and some various constants that really are not going to matter for these lectures, but I'll just write them out for concreteness, related to the MS bar renormalization scheme. Okay? So these are the Feynman rules we need. This is a minus sign because in Euclidean signature, you have e to the minus action. And so when you expand that exponential, you get minus signs in front of everything. Okay, so let's look at this correlation function. And let's look at the one loop correction to it. So of course, at tree level, it has a tree level contribution, which is just this graph. So this is phi squared, this is phi and phi. And this is just equal to 2 times gf of x minus y, gf of x minus z. Can anyone tell me where the 2 comes from? Speak up. Very good. Yeah, exactly. We have 2 phis. So when we do Wick contractions, we get 2 contributions from the different phis in here that this phi can contract with. Okay, so this is tree level. So now let's look at the first one loop correction. So at one loop, we have a graph that looks like this. So this is equal to minus lambda mu twiddle to the epsilon. That's our vertex factor. And then we have an integral over this point, which I can call w. So an integral dw gf of x minus w squared, gf of w minus y, gf of w minus z. And the idea is that in this integral, there's a UV divergence coming from the region where w approaches x. So as w approaches x, there's a UV divergence. And to pick out the coefficient of that divergence, we can just substitute x for w in these two expressions here. Right? W is getting close to x. So here we just substitute w equals x, and then these don't participate at all in computing the divergence. The divergence happens from the integral of this part of the expression. So we can plug in our formula for the Feynman propagator. And we get this integral dw over x minus w to the 2 times d minus 2. And then what it multiplies is just the tree level answer for the 3-point function. So we can write it like this: phi squared of x, phi of y, phi of z, tree. Okay? And then for this integral, we want to pick out the UV divergence coming from w near x. So we go to radial coordinates around x and do the integral. And I'll leave that as an exercise. And the result is that the divergence looks like lambda over 4 pi squared, 1 over epsilon, times the tree level 3-point function. Now again, the idea is that this UV divergence is a symptom of the fact that we're trying to measure the wrong thing. Phi squared is not a good observable in this theory. Instead, to access the good observables, we need to multiply by some factors that cancel the UV divergence and construct what are called renormalized operators. Okay, so we need to construct a renormalized operator, phi squared renormalized, and that's a renormalization factor, and it's conventional to make it to call it z inverse. So z inverse times the Baire operator, and in this case, the value of z that we need is 1 minus lambda over 4 pi, 1 over epsilon. And then plus higher order in lambda. Okay, so we've computed the renormalization factor up to 1 loop. You can do higher order calculations and compute what it is at higher order in lambda. So now the idea is that correlators of this are free of poles in epsilon. And so this thing now lives in the space of good operators of the theory. And it is a thing that we are allowed to measure. But we pay a price for this, which is that the quantum numbers of this object are different from the quantum numbers of the Baire operator. So in particular, the renormalized operator has an anomalous dimension. And you can look up in your favorite QFT textbook what the formula is for the anomalous dimension. And it's the beta function times the derivative of the renormalization factor with respect to lambda. So in this case, this is minus epsilon lambda plus order lambda squared. That's the beta function. That's that formula up there. And then times this derivative with respect to lambda gives us minus 1 over 4 pi squared 1 over epsilon plus order lambda. And this is really wild, but the epsilon term in the beta function really matters here. Okay, you've got to keep it to get this correct. And the epsilon here cancels the epsilon here. And we end up with a formula for the anomalous dimension plus higher order in lambda. And this spectacular cancellation between poles of epsilon actually happens to all orders in perturbation theory. It's something you can prove. And it requires actually a really intricate interplay between divergences associated with the beta function and the local operator, which are actually true. And it's interesting to explore these a little bit, but it works. So to all orders in perturbation theory, the 1 over epsilon poles will cancel in this quantity, and you end up with this finite anomalous dimension. Okay? So that's the story for local operators. We have a nice non-perturbative characterization of them. And then in perturbation theory, the way it works is that the naive point-like measurements you try to make are not well defined. They're UV divergent. So we have to do some work, and that work depends on the theory, to construct the good observables. So by now, we have evidence that a similar story is true for detectors. Okay? So I want to make an analogy with local operators. The idea is that each theory has a space of detectors, which are the things, roughly speaking, those are the things that you could measure in a collider experiment. The things that you can measure are theory dependent. You don't get to decide them beforehand. They depend on the theory, and to figure out what they are, if you're working in perturbation theory, you have to do some calculations. You have to construct some Baire detectors. The Baire detectors will have divergent expectation values. You have to renormalize them to find the good detectors. And when you do, you finally land in the space of things that you're allowed to measure. So let me write this down as an analogy. So we can have, on one side, local operators. And on the other side, we'll have detectors, or light ray operators. So first of all, a local operator is, roughly speaking, something that you can measure at a point. The Baire local operators that you might try to construct will have UV divergences. You need to renormalize them. When you do, the things that you get are theory dependent. In particular, their quantum numbers are theory dependent. And then there are various nice structures on the space of local operators. For example, there's an operator product expansion, which you can use to do calculations. And all of these things fit into this beautiful non-perturbative framework of radial quantization. So in the case of detectors, I want to claim that most of the same thing is true. So first of all, a detector is something that you measure in cross sections, scattering cross sections. When you try to measure Baire observables, they in general have IR and collinear divergences. And so you need to renormalize them. When you do, the detectors that you get depend on the theory. And then finally, when you land in the space of good detectors, they should have some nice structures. And to some extent, there's been work on characterizing a kind of OPE between detectors, so-called light ray OPE. And I would say that this is still very much a work in progress because it's really only understood in special cases. And maybe we'll have some time, I hope we'll have some time to talk about the light ray OPE. Another thing that's very much work in progress is we do not have a good general non-perturbative characterization of the space of detectors in a CFT. So the analog of radio quantization in this story is very much missing. However, by now there's a lot of evidence that such a space should exist and make sense. And I'll talk a little bit about some of that evidence over the course of these lectures. Okay. Questions? Yeah.
The IR divergence is here because we are measuring all of this at null infinity.
Yeah, that's right. So the question was, are these IR divergences because you're measuring them at infinity? And that's exactly right. And in fact, in a conformal field theory, there are symmetries that map infinity to finite positions. And when that happens, IR divergences get mapped to UV divergences. So in CFT, there isn't really, you shouldn't think of really a distinction between these two things. They look like they look like they're unrelated, but in conformal field theory, they're the same. Great question. Other questions? Yes.
Is this light rate OPE connected to this in celestial stuff?
Good. So the question was, is there a connection to celestial CFT? Right. There are probably many connections to celestial CFT. One distinction that I'll point out is in celestial CFT, often people are interested in studying amplitudes. And this is more of a story about cross-sections. So the idea is that you can compute an amplitude, but once you have the amplitude, if you want to know what you measure in a collider, you still have to square it and integrate it against some weight. And the point is that you don't get to choose, you have to be careful about what you integrate it against. The things that you're allowed to measure from the squared amplitude are actually constrained and they're theory dependent and they live in this space. So celestial CFT is all about using conformal symmetry, is in part using conformal symmetry to organize amplitudes. And we're going to see a lot of connections to that a little bit later because we are also going to use conformal symmetry to organize these detectors. But the things that people have been computing are maybe not the same at this point. Yeah?
So although we are working with a specific example of 5 to the 4 theory, like can we extract any universal physics from this light ray operators maybe by going to the large spin limit? Because we know that like dynamics of any CFT are described in the large spin limit are described by mean field theory, right? So can we do something like that for light ray operators?
Good. So the question is, can we extract any universal physics from properties of light ray operators in just phi-4 theory? So can we study phi-4 theory and then learn something that should be true in general CFTs? I think the answer to that is yes. There are Reggie trajectories in phi-4 theory that have analogs in arbitrary CFTs, and we'll talk about those a little bit. Yes.
These are a weight question, but do they contain same information, or is there a difference between information contained in say local operators and other light ray operators?
Great, that's a great question. Okay, and in fact, that's something I should have mentioned. So the question was, do they contain the same information as local operators, or is there somehow more information or less information in the space of detectors? So the space of there's a sense in which the space of detectors contains and extends the space of local operator data. I don't want to say the space of local operators, because what they really contain is the space of null integrated local operators. But the conformal data associated with that is the same as the data of local operators. So if you know so basically what happens is that the scaling dimensions and OPE coefficients of local operators become scaling dimensions and OPE coefficients of detectors in a way that I'll talk about. And those are a subset of the full space of detectors. So the space of detectors is somehow bigger. But at the same time, it's determined by the local operator data. So this shouldn't be that surprising because the local operator data is itself overdetermined by crossing symmetry. But yes, I would say the space of detectors is bigger, but also more rigid in a way. And I hopefully I'll try to make that clearer as we keep going. Yeah.
Since you define this Leiter operators by integrating the stress tensor around null rays, like a particular Leiter operator, say.
Okay.
So like if we assume something like an average null energy condition, then this is like a positive operator. Is that right? Like can I use it to derive any constraints?
Good. So the question was, isn't the null integral of the stress tensor a positive operator because of the average null energy condition? And yes, it is. The average null energy condition implies that this E2 is a positive operator. And in fact, you can show that the entire Reggie trajectory, E sub j, first of all, you can, there is a way to make sense of that in a general CFT. Maybe we'll have a chance to talk about that. That whole Reggie trajectory consists of positive operators. And there are potentially some constraints that could come from that, but there hasn't been a lot of exploration of the consequences of positivity for other operators on the Reggie trajectory. But the average null energy condition has lots of interesting consequences. Other questions? Yes? Good, yeah, that's a great question. So the question is, how do you measure these in cross sections? So there's a non-perturbative formulation of what a collider is doing, and then there's the question of how it looks, what that looks like in terms of perturbation theory in the language of amplitudes. And I'll just try to sketch it here because we're going to see this in more detail a little bit later. But the idea is the following. So non-perturbatively, what you're doing is you have some initial state, you have some state, and you're measuring the expectation value of a detector D in that state. Okay, so this is the non-perturbative model for a collider. And then if we want to get closer to the language of amplitudes, what you would do here is insert a complete basis of scattering out states here. So you would have psi, and then you would have your scattering states. And you would do the same thing on the other side. Okay, and so these are the matrix elements of the detector in scattering states. And for many detectors, these matrix elements are its matrix elements are simplest in terms of scattering states. So for a lot of the examples we talk about, these will be some simple quantities. And I want to think of these as the weights. Whoops, I didn't spell weights correctly. These are the things that you weight the cross-section with. So another thing you might try to do is take psi to be itself a scattering state, a scattering in state. So when you do that, this becomes P1 through Pn, and then you have some initial state, K1 through Km. And then here you have the complex conjugate of that. And this is so these are in states, these are out states. This is an S matrix element. Okay, so in the language of perturbation theory, you end up with an expression for this thing in terms of a sum over these p's, these final state momenta of some weights times the square of a S matrix element. So that's what I mean by measure in a cross-section. So this matrix element literally becomes the integral of a cross-section times something. And the point is that the something that you choose here depends on the operator you're trying to measure. And you're not allowed to pick anything you want. You have to pick the good measurements of the theory. It's an alternative way of thinking about well, okay, let me say a little bit more about this. So what are these good detectors good for? So we could ask a similar question about local operators. What are good local operators good for? And the idea is that the good local operators of the theory are a basis in which you should expand any point-like measurement, or any measurement in a small region. So if you have some kind of measurement, I like to draw a cartoon of a hammer hitting your CFT, or your QFT. So your hammer hits the QFT somewhere. You should expand this as a sum of local operators, where the things that appear in the sum are the good local operators of the theory. They're the ones that, they're the point-like measurements you're allowed to make in your theory. So similarly, if you have a detector, like some kind of camera, so if you have a camera, this thing should be expanded in the good detectors of the theory. And the nice thing about this expansion is it cleanly separates the details of the experiment from the details of the theory. So what you find is that when you hit your QFT with a hammer and then measure things with the camera, that is some kind of matrix element in your theory. And what you should do is write it as, in terms of this expansion, sum over C sub I, O sub I acting on the vacuum state, sum over D sub J times the good detectors, and then sum over I prime, C sub I prime, O sub I prime. You should write it like this, and then expand everything out, and you get a sum over I prime, I, and J of these coefficients which depend on the experiment. So these depend on the experiment, times these beautiful clean things that just are properties of the theory. The matrix elements of the good local operators, the matrix elements of the good detectors in states created by good local operators. These are things that you know make sense, that should make sense non-perturbatively, and there are things that a theorist could go and compute. These are things that an experimentalist could try to determine about their machine, and then you get this nice, beautiful separation between these quantities. And that's what this is good for. So I want to advocate that we should all try to compute the operator product expansion of the LHC in terms of a sum over the good detectors of the standard model. And one of the beautiful things that happens in this kind of expansion is that you can use symmetries to organize the operators here. And then those symmetries tell you a lot about these matrix elements, which in turn tells you a lot about the result of the experiment. Questions? Tom? Absolutely, yes, that's right. So this is indeed what people do in QCD, there are names for these various objects appearing in these cases, and so they don't try to measure bare detectors. They try to construct IR and collinear safe combinations of cross sections to compute. And similarly, these questions about PDFs have to do with relations between scattering in states and out states and the operators that create them. And those things can also be separated into things that make sense, that are properties of the theory, and things that depend on the experiment. So all of these things, yes, are done in the QCD community, absolutely. David, there's about 12 minutes. 12 minutes, okay, good. All right, so that's the end of the sort of extended introduction. Hopefully, it got you interested in what these things are. And now we're going to continue to explore them in a little bit more detail. Yes?
So, we have two CFTs sharing the same local operator spectrum with different space.
So the question is, can you have two CFTs with the same local operator spectrum but different spaces of detectors? I think, I don't know the answer. I think it depends a bit on how much you allow yourself to extend the space of detectors. So you can certainly have two CFTs with the same spectrum of local operators but different spectrum of line operators. So you could try to take a line operator and put it along a null array and define a detector in that way. I don't immediately know examples of that where the line operator can be gauge invariant at the same time. But there might be examples of that. I have to think about it. So naively, if you do this in a gauge theory, you have to do something at the ends of the detector to make it gauge invariant. So you could stick matter fields at the ends, if you like, and that maybe that would define an appropriate such detector. But you would have to have such matter fields available in the theory. And then, for example, your line operator couldn't be charged under one-form symmetry. So I don't know if that affects the story. But that's a great question. I don't know the answer. Other questions? OK, so all right. So what I want to do next is start to develop some technology for understanding the symmetries of these things. OK. So first of all, we're going to demand that detectors be translation invariant. So physically, the idea is that it's something that is that the length scales and time scales associated with the collider should be much, much longer than the length scales and time scales of the thing that it's measuring. This is certainly true in practice for physically, it's usually often true in practice. So this is a natural thing to demand. I'm going to try to write my detectors as curly Ds to distinguish them from the dilatation operator. In a CFT, there's a nice way to phrase this. This means that the detector is a primary at spatial infinity. So just to remind you, a local operator at the origin is primary if it's killed by the special conformal generators. In a CFT, you can define a local operator at infinity using an inversion. Another way to think about it is it's a particular limit as the local operator goes to infinity along some direction. And when you do that, a primary operator at infinity, instead of being killed by k, it's killed by p, which is the image of k under an inversion. So the momentum generators are the image of k under an inversion. And so this means that a primary operator at infinity is killed by p. So a detector transforms like a primary operator at infinity. In a CFT, we can also ask what the scaling dimension of a detector is. And that's just its eigenvalue when we act with the dilatation operator. And then the last thing that we can do without loss of generality is impose that a detector transform in an irreducible representation of the Lorentz group. Okay, so So it's going to have some scaling dimension. The scaling dimension, because it transforms like a primary operator at infinity, it's natural to define the scaling dimension with a minus sign, like this. And this is based on the situation with a local operator, where if you take a commutator of the dilatation operator with a local operator at infinity, this is minus delta for the local operator. Okay. And then finally, it has to transform in an irreducible representation of the Lorentz group. Which is of course SOD minus 1, 1. This condition is interesting, and we're going to have to spend a lot of time with Lorentz representations in these lectures. So I'm going to take some time to develop technology for talking about these irreps. Okay, so that's what we're going to do next. We're going to talk about representations of the Lorentz group, and hopefully build a language that will make it easy to think about these detectors. For example, these E sub j detectors that I talked about before, we'll be able to understand their Lorentz transformation properties very simply. So I'm going to start with something hopefully familiar, which is tensors, and write them in terms of what's called index-free notation, which at first will just look like a kind of nicety, but will turn out to be really crucial for describing the more complicated types of representations that will arise in this story. So let's start with a traceless symmetric tensor with spin j. So this is a tensor with j indices. It's symmetric. And traceless. So tracelessness means that if we contract any pair of indices with the metric, then the result vanishes. So this is tracelessness. Sorry, my handwriting degrades as I go farther down on the board. Okay, so the idea of index-free notation is that we can encode this tensor in terms of a polynomial. And this encoding is often a lot easier to think about. And in fact, it's also more efficient, for example, if you're doing calculations in a computer algebra system or something like that. It's just a better way to think about tensors. So, oh, by the way, I should say, before I do that, this type of representation, we can associate a Young diagram to it, which basically it's a diagram of how the symmetry structure of the indices. So the Young diagram for this representation is a row of j boxes. And the idea is that rows represent groups of symmetric indices. So this is a single group of j symmetric indices, so it gets a row of j boxes. And I'll sometimes write this representation as just j in parentheses. Okay, so the idea of index-free notation is to introduce an auxiliary polarization vector. So this is sometimes called a polarization vector. And build a polynomial by contracting all of the indices of t with this polarization vector. So first of all, we're exploiting the fact that t is symmetric by using the same polarization vector for all of the indices. So we're contracting with the same z, but we didn't lose any information because t is symmetric. Furthermore, because t is traceless, we can impose that z is null. So what do I mean by that? So I mean that if someone hands you a t of z, a polynomial t of z, there is a unique way to reconstruct the traceless symmetric tensor t mu1 through mu j from that t of z. how does that work? Well, the idea is if we start with T of z, we want to strip off the z's, right? So we can do that. But when we strip off the z's, because z is null, the result after stripping them off is ambiguous up to terms proportional to the metric. However, all the terms proportional to the metric are fixed by tracelessness. So maybe it's best to see an example. So for example, if you had T of z of this form, a dot z squared. So first of all, this is a rank 2 symmetric tensor, and I know it's rank 2 because this is a quadratic polynomial in z. So then we could try to reconstruct the underlying tensor, and to do that we have to strip off the z's. So T mu nu, that, well, naively we get a mu a nu, but then we can have anything we want times the metric, a to mu nu. But there's only one thing we can write that gives a traceless tensor, which is minus 1 over d, a to mu nu, a squared. So this is the idea. There's a one-to-one mapping between these polynomials in a null vector and traceless symmetric tensors. In the notes, which I'll post after the lecture, there's an exercise about a more sophisticated way to reconstruct these polynomials, to reconstruct the tensor from the polynomial that works in complete generality. Okay, so if you're interested in that, you can check out the exercise. Good. So, okay. So the idea is that a spin j traceless symmetric tensor is equivalent to a degree j polynomial in a null vector. And so we can use this, for example, in the case of local operators. If you have a spin j local operator, then we can contract each index with an auxiliary polarization vector to form what I'll call O of x comma z. And one of the nice things about doing this, well, one nice property of this operator is that it transforms in a very simple way under a Lorentz transformation. So if I set x to 0 and I hit this with a Lorentz transformation, then z just transforms linearly. Okay. All right. Very good. Can I take 2 more minutes? Okay. All right, so now that we have a little bit of this language, we're ready to look at the Lorentz transformation properties of the detectors in the free theory that we defined earlier. So let's do it. So the idea is that to make their Lorentz transformation properties manifest, we want to write them in terms of something that transforms linearly under Lorentz transformations, i.e. a polarization vector z. So before I was writing it as a function of n, but now I want to write it as a function of some z. And I'll write the formula and then explain it. So this is just the same integral as before. But now we use z instead of n. Where z is a vector, a 4 vector. Okay, and if we set z equal to 1 comma little n, then this recovers the same formula as before. Okay, so this is just a different way of writing the same operator. One nice thing about writing it this way is that now its Lorentz transformation properties are completely manifest. This z just transforms linearly. Okay, and that is because I chose these creation and annihilation operators, you might remember, so that they transform in a simple way under Lorentz transformations. So I'm just using that formula. And so then finally, to figure out what representation this is, we should just look at the degree of homogeneity in z, right? So up here, when we had a tensor, the way we know what representation it is, when we have a polynomial t of z, we know what representation it is by checking its homogeneity. This was a quadratic polynomial, so we knew it was a rank 2 tensor. So now let's check the homogeneity of this thing in Z. And the idea for doing that is that in order for this combination to make sense, E has to have degree -1 in Z, right? In order for this combination to make sense. And so then you trace that through here, and you find that E sub j of lambda z is lambda to the 3 minus d minus j times E sub j of z. So what this means is that this detector we defined corresponds to a single row Young diagram with length 3 minus d minus j. So I have to put length in parentheses here, or in quotes. So we have a continuous spin traceless symmetric tensor. So in index-free notation, these things are not so mysterious. A continuous spin traceless symmetric tensor is just a homogeneous function of a null vector where the homogeneity is non-integer. The price you pay is that there's no underlying tensor anymore. There's no t mu1 dot 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 mu j. That doesn't make any sense when j is not a positive integer, not a non-negative integer. So there's no underlying tensor anymore, but the same representation makes sense, and we can use this same notation for it, and we can understand how Lorentz transformations work in the same way. Okay, so what we have is a continuous spin representation of the Lorentz group, and we're going to be seeing a lot of this. In general, to describe the representations for these kinds of detectors, you need these Young diagrams with funny row lengths. But we'll also see next time that these are not so unfamiliar. So you've actually seen a lot of these before, and so that's what we'll do next time. Okay, so I'll stop here. Thanks.
David, it's a little late. Maybe we have time for one question. Yeah, go ahead.
So maybe this is not relevant to CFTs, but when you construct these observables in the standard model, for example, I might imagine that you would get something like, oh, in your detector, you might see a top interacting with something as an observable. But then when you actually have the physical experiment, the top is always going to decay before it's an experiment. So will you, like when you do this operator product expansion, is there some, can that somehow account for the fact that things will decay and not really be detected?
Yeah, so, right.
Could you repeat the question?
Okay, so the question was, does this operator product expansion account for the fact that certain things will decay before they reach the detector? Like, for example, a top will decay into various other things. So I think that this, in the context of a non-CFT, a way to think about the operator product expansion is in terms of effective field theory and running and matching. So the idea is that when you have a process, you have to figure out what the relevant energy scales in the process are. And if the energy scales are different, you need to follow the procedure of running and matching starting from the highest energy scale down to the lowest. So the operator product expansion is kind of like a matching computation. For example, if you have a bunch